Students, today we are going to discuss about the quantum mechanical model of atom. The motion of all macroscopic objects such as falling stone, moving car, orbiting satellite, etc. can be successfully described in terms of the classical mechanics based on the Newton's law of motion. These objects predominantly have the particle character. However, a microscopic object such as electron has both observable wave-like and particle-like properties. The behavior of such particles cannot be explained on the basis of classical mechanics, which is based on Newton's law of motion. In order to explain the behavior of electrons and other microscopic particles, a new branch of science called the quantum mechanics was developed. It is a theoretical science that takes into account the dual nature of matter. Based on the quantum mechanics, a new model of atom was developed during 1920s, and this model is known as quantum mechanical model of the atom. Now, what is the chance of finding an electron in the nucleus? This is the question here, that what is the chance of finding an electron in the nucleus? Now, the quantum mechanical model just tries to explain it, right? Now, it states that the electrons are not in a circular orbits around the nucleus. Electrons are in a 3D regions around the nucleus called atomic orbitals. The atomic orbital describes the probable location of the electron. Now, from the quantum mechanical model, we get the concept of the atomic orbitals. Now, you can see in the diagram here that the Bohr's model, right? Bohr's concept has brought that at the center there is the nucleus, which consists of the protons and the electrons, right? They will be revolving around the nucleus in a fixed path, right? But it has not, we can say, it is just not able to explain the dual nature of the matter, right? That the wave-like characteristics of the electron. Now the recent, that is that the nucleus will be at the center and there's an electron cloud which is around the nucleus. So from where does this model come from? A quick history. Louis de Broglie has gave the concept that electron behave like a wave and particle properties at the same time. That is, the concept of the matter wave was given by the de Broglie. Then comes the Heisenberg uncertainty principle, according to which it is impossible to know both the position and velocity of an electron simultaneously. Then the Erwin Schrödinger plays a very important, we can say, role, right, to describe the behavior of electron in an atom. He gave the Schrödinger wave equation. He refined the wave-particle theory proposed by the de Broglie, developed an equation that treated an electron like a wave, and predicted the probable location of an electron around the nucleus, called the atomic orbital. Now, on the basis of the wave mechanical concept that definite energy levels are present in an atom. Now, the important features of the quantum mechanical model of atoms are, please just listen it very carefully. The first feature is that the energy of electron in atoms is quantized. That is, electron can have only certain specific values of energy in atoms. Second, the existence of quantized electronic energy states is a direct consequence of the wave properties of electron. The wave property of electron gives us the existence of the quantized electronic energy states in an atom. Third is the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. Therefore, it is not possible to determine the exact trajectory of the electron in an atom, and this gave rise to the probability concept of finding the electron at different positions in an atom. The fourth is the psi for an electron in an atom represent an atomic orbital. An orbital is associated with a definite amount of energy. Since many wave functions are possible for an electron in an atom, there are many atomic orbitals in an atom. An orbital cannot contain more than 2 electrons. All the information, this is the fifth feature, that all the information about the electron in an atom can be obtained from the orbital wave function psi. Sixth is the probability of finding an electron at the point within an atom is proportional to square of the orbital wave function psi square at that point. Psi square is known as the probability density and is always positive. Now, what is the significance of psi? The moving electron is associated with a wave, and the wave function psi gives us the amplitude of the electron wave. It has no physical significance, whereas psi square has a physical significance. It helps us in assessing the probability of electron in a particular region. Hence, psi square is called the probability density and psi is referred as probability amplitude. Students, we are going to discuss here the graphical representation of the probability of the electron or probability density with that of the distance from the nucleus. So we will start with them with the electron density. There are two ways to visualize the electron density based on the dual nature of matter. Remember that all matter, including the electrons, behave as if it is both a particle and a wave. Depending upon what we are measuring, sometimes we observe the electron behaving as a particle and sometimes as a wave. Now you can see here a graph. This is the electron density graph for the 1s orbital. Here on the x-axis we have radius and along the y-axis we have written here electron density. If you just try to understand this graph here, when the distance from the nucleus for 1s orbital, right, it is lowest, least, that time the electron density is maximum. But as the distance from the nucleus increases, that means we are increasing the radius of the 1s orbital, what will happen? There will be decrease in the electron density, right? A moment will come when it will have the minimum value for the electron density. Now here you will see the another graph. Here we have represented the 2s orbital. Now here it is same, but you can see here that here is a point at 100, right, where there the electron density becoming 0. Now student, this point, this drop point is known as the node. And right, we'll see that in the beginning when the distance of the 2s orbital from the nucleus, right, is less, that time the electron density is maximum. But as we start moving away from the nucleus, as the distance from the nucleus increases, there is a fall down in the electron density. It falls to such an extent it becomes 0 at point here we have considered to be 100, right? And then again when the distance from the nucleus increases, then it is an increase in the electron density. Now we have gone through the two graphs, right, for 1s and 2s. Now we will compare these two graphs for 1s orbital and 2s orbital. You can easily find the difference that in 1s orbital we were not having a node area, whereas in the 2s orbital we are having a node, and after achieving a node, right, it again rises up, right, and then again falls down, right. Now in hydrogen 2s orbital, right, we are having at point 100 a node has been obtained. A node is an area where we have got probability of finding an electron is 0, right student. Now the node in a 2s orbital is actually a spherical surface whose radius is 105.9 picometer. We are considering it to be for the hydrogen. The picture below shows a cross section area through the 2s orbital where the gray shade is indicating the electron density, whereas the dotted line, right, is showing the surface, spherical surface, where the electron density is 0. Now all the s orbitals which are similar to the 1s and 2s orbitals in having their highest electron density at the nucleus and dropping off to 0 as the distance becomes very large. However, the higher s orbitals like 3s, 4s, 5s, etc. extend farther from the nucleus. They will be more away from the nucleus because they are bigger in size. Also, higher s orbitals have additional nodes. All these nodes are the spheres centered on the nucleus, and we call these spheres to be radial nodes because they are fixed at radii from the nucleus. Now you can see here that earlier we have seen the cross section of 2s orbital where we are finding only one surface, a nodal surface. Now here we will find two nodal surface for 3s orbital. This orbital has got two radial nodes, two spheres shown in red, right. Now this is the electron density curve for the 2p orbital, right. Now here you can see that when we are closer to the nucleus, or when the 2p orbital is very close to the nucleus, that time the electron density is minimum, and as we move away from the nucleus, the electron density increases, reaches its maximum value, and then there's a fall in the electron density of the 2p orbital, right. So for the 2p orbital we are not having any node, but when we will draw for the 3p orbital we will have one node over there, right students. So radial node, how we can find out the radial node? The radial node formula is n minus 1, where n stands for the principal quantum number. By subtracting the 1 we can find out the number of the radial nodes, right. So if we have got the orbital 3s, right, so here the number of the radial node will be 3 minus 1, that is 2. The shapes of the orbitals can be represented quite accurately with the help of boundary surface diagrams. In this representation, a boundary surface, also known as contour surface, is drawn in space for an orbital on which the value of probability density is constant. A boundary surface which encloses the region of maximum probability, say 90%, describes the shape of the orbitals. It is not possible to draw a boundary surface diagram which encloses the region of 100% probability because probability density has always some value, howsoever small it may be, at any finite distance from the nucleus. The boundary surface diagram for s orbitals are spherical in shape. The size of the s orbital, however, increases with increase in the value of n, that is the number of the principal quantum number. If we observe the probability density curve for 2s orbital, we find that the probability density function for 2s orbital decreases to 0, increases to maximum value, and finally approaches 0 with increase in distance from the nucleus. The region where the probability density function reduces to zero is called the nodal surface or a node. So we have discussed earlier that the 2s orbital has only one node. So in any ns orbital, the total number of node is n minus 1. So you can see in the diagram here that the boundary surface diagram for 1s orbital and the 2s orbital. Now in the 2s orbital you can see that there is a region where there is no uh, electron density, right, and that is the node, and that can you can see there is a clean zone, right. At the center we have got the nucleus, which is shown by the black dot, right. It's a representation. Now surrounding it you can there will be electrons, and then the area will come where there will be no electron density, right, and that is shown by the clean zone. And you can see that the center there is a dark grayish zone, which is representing the electron density to be high near the nucleus, and then as we are coming away from the nucleus, it is getting decreased. A point will be reached where there will be no electron density, shown by the nearly clear zone, and then finally again we will have the electron density observed by the dots, right. Okay, now next we will see for the boundary surface diagram of the 2p orbitals. You can see that here we don't have a spherical shape. Each orbital consists of two lobes which are separated by a region of zero probability called node. The three 2p orbitals lie along x-axis, y-axis and z-axis respectively are designated as 2px, 2py and 2pz. Like s orbitals, p orbitals are also increases in size with increase in the value of n. However, higher p orbitals have nodal surfaces in addition to the nodal plane. The number of nodal surface in any np orbital is given by n minus 2. Thus, a 2p orbital has no nodal surface, whereas a 3p orbital has one nodal surface. Now let's see the boundary surface diagram for the 5d orbitals, which are designated as dxy, dyz, dxz, dx square minus y square and dz square. The boundary surface diagram of 5 3d orbitals are there in the diagram here. The shape of the first 4d orbitals, that is dxy, dyz, dxz and dx square minus y square are similar to each other. Each of these orbitals has got the four lobes, and the fifth d orbital, that is dz square, has different shape. All the 5d orbitals have equal energy. The higher d orbitals also have similar shape but differ in size and energy. Each d orbital has got two nodal planes or angular nodes. So students, here the nodal plane indicates the angular nodes. For example, dxy orbitals has got two nodal plane passing through the origin and bisecting the principal axis. Higher d orbitals have nodal surface or radial nodes in addition to the angular nodes, right. In any orbital, the total number of nodes is equal to n minus 1, and the angular node or the nodal plane is equal to the angular momentum quantum number L, and radial node will be equal to n minus L minus 1, right. So for 3D, let us take the 3D orbital. Now in this case the 3D, right, the total number of nodes will be equal to n is here 3, so it is 3 minus 1, that will come 2, whereas the angular node or the nodal plane will be equal to the angular momentum, right. So it is here the value for 3D. What is the value of L here? It is 2. So number of the angular nodes will be 2, right? And the radial node will be equal to 3 n minus L minus 1, that is 3 minus 2 minus 1. So 3 minus 2 1, so 1 minus 1 equals to 0.